Hello, Lucia. Welcome to the stream. Today we're going to be doing the weekly contest 395. So let's get started. Q1. Nice. I haven't done that one. Well, I don't want to spoil it, but you can learn something. So it seems that Q1 and Q2 are the same, but they're not actually the same. Find the integer added to array 1, to array part 1. You are given two arrays of equal length, nums1 and nums2. Each element in nums1 has been increased or decreased in the case of negative by an integer represented by the variable x. As a result, nums1 becomes equal to nums2. Two arrays are considered equal when they contain the same integers in the same frequencies, with the same frequencies. Return the integer x. Okay, so do you understand the problem? Is the problem clear? So here we have what's up, how's it going? So here we're told that the element that was added, the value was x, the value of x here is 3. So you add 3 to 2 to get 5, then 3 to 6 to get 9, and then 3 to 4 to get 7. So the order doesn't matter. Smart coder, welcome. So you have to ignore the order here. You have to think about this as multisets, I think, because there can be repeated values. That's why I'm talking about multisets. So is the problem clear? So one thing to notice here is that yes, great. One thing to notice here is that when you add a constant, you add this x value to each of the elements of nums1. The minimum is going to be the same element. So here you add 3 to 2, so 2 is going to still be the minimum value, right? Because you're shifting all of them by x. So the minimum will still be the minimum. And that minimum is going to correspond to the minimum of nums2. So now we have two values that were transformed. So now we know that the minimum of nums1 plus x equals the minimum of nums2, right? And so we can find x by subtracting why are we considered only the minimums? I mean, we are just you can consider any element, right? Minimum is enough because what I said, you could consider the maximum as well, or the kth element. What I'm saying is that the order of the elements doesn't change when you add a constant to all of them. You're just shifting them, right? So here you have 2, 4, 6. Right, the order remains the same. If you add 6 and you have them in order, then this becomes 8, this becomes 10, and this becomes 12. So here what you can say is that if I get the kth element of n, let's call it this way, of n in sorted order, when we add x, we're gonna get the, well, this should be, sorry. Let's say that our nums is in order. So we have nums 1 at position k plus x is going to be equal to num 2 of k, right? And so we can do the same we did here to get what x is, but it's easier to just get the minimum instead of the kth element. We don't need to sort to get the minimum. So that means that we can do the minimum of nums of 2 minus the minimum of nums of 1. I think this is too small. Cool. So that was an easy one in terms of code. Right? But yeah, the idea is this, that the kth element will correspond to the kth element in nums 1 will correspond to the kth element of nums 2. So you can use both of them to get the value of x. Great. Great. So let's move on to Q2. So this is similar, but it's not the same. You're given 2 integer arrays, nums 1 and nums 2. From nums 1, this is different. From nums 1, 2 elements have been removed, and all other elements have been increased or decreased by an integer represented by the variable x. So it is the same idea, but with 2 elements removed from nums 1. Okay? So we can use a similar idea in the idea of matching the minimum, right? But in this case, we don't know which one is the minimum, because it could be eliminated. It could have been removed. So now we do want to sort. Let's sort nums 1, and we're gonna have so we can consider the first 3 elements as the minimum of nums of 1, right? Because the minimum could be the minimum after the removal, but if it was removed, then maybe it was the second minimum, but maybe the first 2 were removed, and in that case it will be the third minimum. So those are the three options for the minimum value of nums after the removal. So And do we have, so we have at least 3 elements in nums, so that's good. And then we want to match it. We want to find the x value, and if the ith element of nums1 is the minimum, we can do the same thing we did before. Right? So this is going to give us the x if the ith is the minimum. But we have to check if it's valid, right? And how do we do that? Well, first of all, notice that we're asked to find the minimum possible x, and here we are going from smallest to largest. nums1 of I is increasing, but this means, since this is subtracting here, this means that x will decrease. So it's better if we do it the other way around. We go from the largest to the smallest, because the largest nums of 1 is going to give us the minimum x. So if it turns out to this x to be good, then we can then we can just return it, right? If it's good, if x is good, we return x, right? And how do we know if it's good? We have to be careful, because we have to use the counts of the elements, right? We want to check for all the elements in nums1. We want to see, after we add x, we want the count in 2 must be less than or equal to the count in 1, right? Because there could be removals, right? So in count 2, there cannot be more than this. And I think this should do it. Okay, so here I have my x. And I want to transform. Oh, it's the other way around. It's the other way around, right? Because I want, so yes, because the numbers in count 1 can be yes, actually, so I want to check that all the numbers in nums2, when I subtract x, the numbers that we had in counts 1 were greater than or equal to the numbers that we have in count 2. Let's see if this one works. Yep. Cool. Yeah, I got a little confused here. But yes, the idea is that, so let me maybe review this so that it becomes clear. So in this example, can you summarize? Yes, exactly. How do I? Okay. So here the answer is -2. Right? So how do we get this? Well, there are no duplicates here, so it's a little. So what we did first, we sorted. So here we would have 4, 8, 12, 16, and 20. So this is nums. So one thing that the first observation was that the minimum after the removal, the minimum must be one of these three, right? One of the three minimums, right? Because it's not necessarily 4, right? Because maybe 4 was removed. It's not necessarily 8 because maybe both 4 and 8 were removed. So it could also be 12. So we can try the three options, right? So let's say that we try 4. So let's say we say the minimum of 1 is 4. Then we can match, as we did in the previous problem, the minimum of 2 is 10. So that means that after we added x to 4, we got 10. So that means that x must be 6. Okay, so this is a candidate for x. So now we want to check if it's true, if it's all consistent, right? So what do? We want to see if we do the inverse to all the numbers in nums2. So we go over the numbers of nums2, which are 10, 14, 18, and we subtract x. That's going to give us 4, then 8, and then 12. Okay? So that means that nums of 1 must be this plus some other numbers. So what we checked is that this has a 4, this has an 8, and this has a 12. And it does. But so this way we avoided identifying which specific two numbers were deleted. Yes, notice that if we consider one of the numbers to be the minimum and we map that to the minimum of this, then the ones that were less that were less than it will not be in here, right? Because because of how we selected to match the minimums. But here, yeah, here what we managed to prove is that x equals 6 it's actually a candidate, right? But that doesn't mean that that is the answer, because we have to get the minimum x. And apparently it turns out that 12, that if we choose 12 to be the minimum, so if we say, okay, the minimum of 1 is 12, so we're assuming that 4 and 8 were removed, right? So now that means that our x in this case must be -2, right? Because 12 minus 2 gets us the minimum of the second of nums 2. And so now we do the inverse again. So we get 10 minus -2 is 12. 14 minus -2 is 16. And 18 minus -2 is 20. And then we check, and all of them are contained in nums1. So this is also valid. And this is better because it's less than 6. So this is why this is the answer. Okay, so that is the review of what we did. I found this one harder than Q3. Yes, I think you can get confused by the duplicates. You have to handle the duplicates. I did that with counters. This explanation made it much clearer. Thank you. Great, that's great. Okay, all right. So now I don't know why. I think I selected C++ for some other problem. Okay, so minimum array end. My first intuition would have been to sort both. Yeah, I guess you could do it with sorting instead of the counter. But the thing is that you will have to skip elements if you want to like go with 2 pointers on each list and match them. You have to skip elements, so that would be a little messy, I think. So doing it with the counter, you have to realize this condition, which is what confused me. So it's not trivial, but it's not a big deal. So let me share this one. Let's do Q3. Minimum array end. You are given 2 integers, n and x. You have to construct an array of positive integers, nums of size n, where for every... So, well, here it means that it is strictly in strictly increasing order, right? So nums of I plus 1 is greater than nums of I. And then the result of the bitwise AND between all elements is x, which is a given. Return the minimum possible value of nums of n minus 1. So let's think about it. So we have n equals 3 and x equals 4. So notice, well, it's easier to think whenever you have to do bitwise operations, it's better to think in terms of bits. So 4 is 1, 0, 0. Okay, so notice that all the numbers, so we have to find an array of 3 numbers, right? So let's put it down here, and their AND, so if we do the AND, has to be 4. So it has to be this. So what does that mean? That means that in the places where the x, so this is x, the places where x is 1, then all of them must be 1, must have a 1, right? Because otherwise the AND would be 0. So that's just forced. And then we have to fill in the other digits of these numbers, right? So let's say they go from, so let's say this is the 0 element, the 1 element, and the element at index 2. So we want to minimize this value, but they're strictly in order. So maybe we can set the smallest value here. The smallest values would be to set all zeros in the other digits, right? That would be the smallest one that we can get. And that guarantees, notice that guarantees that the AND is going to be exactly x, right? Because since on each column, this row, there will be a 0. So if there's any 0 in the column, the AND will be 0. So this is also 0, right? So now we're sure that we're complying with the AND requirement. And so now what can we set? So notice that we can set, so here if we ignore this, let's say that we ignore this now for a moment. Let's say that we pretend that this is not here. Then we obviously want to set the minimum numbers here. So here we set 0, then here we set 1, and then here we set 2. And this is going to make it increasing, and it's going to make it as small as possible. So that is the idea. Notice that if we had, so if we had number, so if x equals 9 and n equals 5, so we would do something similar, right? So we would have, are there any questions? Am I making sense? Yes. Okay, so 9 in binary is this, right? So like we said, we set all the ones here. These must be ones. This is index 0, 1, 2, 3, 4. Then we forget about these columns. And we set we set 0 here. We set the index number here. So 0. 0 is all 3 zeros. Then here, 1 is 1, 0, 0. Then 2 is 0, 1, 0. Then 3 is 1, 1, 0. Then 4 is 1, 0, 0. Okay? So this is the algorithm. So we have to do a bit of bit manipulation to do this, but it shouldn't be too hard. So we're gonna go from, so we can generate directly the last number. Yes, that's what we're gonna do. So yes, we essentially want a number that has ones. So here is, I didn't mention that, but so this number here is n minus 1, right? So we basically want to generate a number that has ones in the places where x has ones, and then in the rest of the digits has the bits of n minus 1. So here it is 4, so here if it was something like this in this case, but this is for a different number, if x was 10, then you would have ones in here, and then we would have 4, which 0, 0, 1. So yes, that's what we're trying to do. So we're gonna process both x and n from the least significant digit. So we want to keep going while any of them still has some bits turned on. And on each iteration, we're gonna shift x one place to the right, and we are also going to have a bit indicating where we are in the result. And so here we want to see if x has a 1 in the current bit, in the current least significant bit. Because if it has, then we just set that, we have to set that to 1, which is we have to set to p. Then otherwise we want to consume a bit of n, right? So again, if the least significant bit of n is 1, then we also want to set a 1, and we want to shift n by 1. And I think this is it. Wait, so I'm shifting 1. So I'm always shifting x, right? Because I'm only shifting n when I'm going to consume a bit from. Oh, it's n minus 1. It's n minus 1. Yep. I think there is a gap between thought process and code. I have no idea what should I do, but I don't know what the. I have an idea what should I do, but I don't know what the code is doing. Okay, let's dive into the code. So let's think about this case. So we have x equal 9 and n equal 5. So we want to combine x, which is, the code is harder to understand than the idea. Yes, I mean, it's not trivial. So here we want to combine. It's like we have two lists. So one list is the 9, which is this, right? This is a sequence of bits of 9. And then we have n minus 1, which is 4, which is this, the 0. You can think about it as we are merging these two lists in a sense. So we have 0, 0, 1, 0. And then we have, on the zeros of this one, we have a 0, a 0, and a 1. So we combine both and we get this. Do you follow what I'm doing here? I want to put this number, the 4, in the gaps of x. The gaps means the zeros. So here we have 9. So we're going to use this place, and this place to put 4. So we put a 1 here, and we put 0 here and 0 here. So this, okay. So how do we do that? We're kind of iterating. I guess you could do it a different way, but we are iterating. At each iteration, we're at 1 digit. So we say, is this digit, is this bit of x 1? In that case, we set a 1 to the result. Right? So that's what we're doing here. If the least significant digit of x is 1, then we set a 1 to rest. P is going to have a 1 in the current bit that we are processing. And then we have the other case where we don't have a 1 in x, and so we want to consume the least significant digit of n. And so if that digit is 1, then we set the current bit to 1, and we consume, like we shift the number so that we go, in the next iteration, we're going to go to the next one. Can you explain your approach once you have solved this question? What do you mean? So notice that shifting to the right is like deleting. You can think of bits. Can you explain me the approach again? Oh, yeah, I mean, I went over a lot, so maybe you can you can watch the video once I upload it. So the summary, so here I have an example. Do you know the problem? So the summary is that you want to generate 5 numbers in this case, and they all have to have x, which in binary is this, as the AND. So that means that in these columns they all have to have ones. So you can ignore that columns. You can forget about them, and then in the rest of the bits, in order to minimize the numbers, you set the number in the index, right? So here you put 0, 0, 0, then you put 0, 0, 1, 0, 1, 0, and so on. So that's the. So there are 4 variables in total. Is it possible to name them a bit clearly? Bit manipulation is particularly hard to understand, in my opinion. So the naming, so P is the only name that I think might not be clear. So X is what is the number from the input that we're going to be shifting to the right. So that means that we're going to be processing its bits from least significant to most significant on each iteration of the while. Then N is the number that we want to, is the number from the input, which is the number that we want to put in the gaps of X. And then P is just it's just indicating. So you could even yes, P keeps track of the place where we want to set the bit in rest, right? Because on each iteration we are shifted. Initially it's 1. Then after each iteration, we shift it 1 to the left. So that's why when we set a bit to the result, we set P. It's just a number with only one bit set. So another option would be to have. Maybe this is clearer for you, so maybe we could have a counter. Maybe we can have an index of the, and here we would do this. Is this clearer? So I is the index of the digit that we're processing. Okay, great. We're deleting the least significant. Thanks a lot, coach. Thank you. We're deleting the least significant bit in X at each iteration, and we are adding the most significant. Yes, that is so much better. Yeah, great. Great. Yes. So again, we are, if there's a 1, then we have to set a, if there's a 1 in X, we have to set a 1 in res. But if it's not a, if there's not a 1, there's a gap. There's a 0, there's a gap, so that means that we have to set the next bit of n, right? So that means that if it is a 1, we set it. If it is not, then we don't set it. And we consume it. We shift only in this case when we are setting the value of n. We don't want to miss any bits here. So only in that case we consume a bit from n. So I think now it's clear. Clear? Okay, great. Cool. So finally, the last one, Q4. Thank you. Find the medium of the uniqueness array. You are given an integer array nums. The uniqueness array of nums is the sorted array that contains the number of distinct elements of all the subarrays of nums. In other words, it is a sorted array consisting of, okay. Return the medium of the uniqueness array. So this one is going to require some explanation because it's a little complicated to wrap your head around it. So maybe we can work this one out. So what we're told is that we have to consider all the subarrays of nums, right? Remember that the number of subarrays, so here n, the size of nums is 3, right? So remember that the number of subarrays is n times n plus 1 divided by 2. Right? Should I explain this? So if you so here, if the subarray starts at 1, then it could end at 1, 2, or 3. So there are 3 possible endings when it starts at 1. If it starts at the second index, then there are 2 ending positions. If it starts at the third element, it has 1 ending position. So that's why it's the sum of the integers from 1 to n, which, as you may know, this is the formula for it. Okay. So here since n is 3, this is 6, right? So there are 6 subarrays. So I guess we can enumerate them. So first of all, you have the 3 subarrays with only 1 element, and the number of elements here is 1, 1, and 1. Then you have this subarray which has 2 unique elements. You have this subarray which has 2 subarray elements, and you have the one with the whole thing, which has 3, right? So they say, okay, consider all these elements, the distinct elements of each of the subarrays, and consider them in sorted order. And then find the element in the middle. Here it would be this one in this array. So the medium. the median with this definition that if the number is even, then you get the smaller one. Okay, but this doesn't matter. Don't worry too much about this. So in general, the median is a special case of finding the kth element. And if you remember from a previous stream, I showed how whenever you have a problem where you have to get the kth element of where you have to get the kth element of some set, what you can do is you can have a count. If you could count the number of elements, so here you have D distinct, which is the number of sub arrays with D or less distinct elements. If you can count this, then you can get the kth element with a binary search. So let's focus on counting that first. So this boils down of doing this. So we have some D here, and we want to count how many subarrays have D or less distinct elements. Hey Pat, thanks for the raid. Thanks a lot. We're doing a contest weekly. We're now on Q4. So we kind of reduce, so bear with me. Let's see if we can solve this problem where we can count the number of arrays with D or less distinct elements. And notice that this is a very classical sliding window problem that you might have solved before. So if you have you have an array of elements, and remember that in the sliding window pattern we have an R of the window, a value of the window, and then we have some L pointer, and we want to add element R to the window, and then we want to check quickly to know how many unique elements there are, how many distinct elements there are in the window, and if there are more than D, then we shrink it, right? So that's going to guarantee that after we shrink it in our window, we would have the longest window that ends at R that satisfies this, that it has D or less distinct elements. So that means that we can add the size of the window to our result. The size of the window is going to be this, because any beginning from L to all the elements between L and R, including R, are going to be subarrays that end at R and have D or less distinct elements. Okay, so this is easy. This is easy. So yeah, I guess this was not a this was on the easy side, I think, in terms of Q4s, in terms of hearts. And so then we just have to do the binary search to find the kth element. So notice that here kth is the median, and so this list has this many elements. Didn't know you streamed too. Yeah, thank you. Thank you, Jiwandi, for the follow. So here, the list has this size, and we want the middle element. So that's going to be this, the number of elements divided by 2, right? Rounded down. Or no, sorry. So here we have 6 elements, right? This is index 0, 1, and 2. So we want index 2. So I think it's 6 minus 1 divided by 2. Integer division. So that's going to give us our index. So it is. So if this is big N, then we want big N minus 1 divided by 2. This is the element that we want to search for. But yeah, let's begin by implementing our count function, which should be easy enough. So let's do it here. So we have count D, which is going to return the number of sub-arrays with D or less distinct elements. Okay? We can do this. This one is easy. So we have nums, we have D. We are going to keep track of the. So we're going to have a window that starts at L. We're gonna have a right side of the window, which ends at R, which is R. And we're gonna also keep track of the count of the elements inside of our window. Okay, so, and we also want to keep track of keep adding to the result. And so here, we want to add nums of R to the window. So we count this number, we add 1 to this value. But now we have to shrink the window from the left to, in case it's invalid. Now if we have more than D distinct elements, so let's say that the count elements, the length of the counter is going to give us how many distinct elements we have. So if now it's greater than D, then we have to remove nums of from count, remove nums of L, and we increase L, right? So we shrink it from the left because now we have more distinct elements that we wanted. And now it's valid. Now that we're here, it is valid. So we have to add all the possible beginnings, which is any element within the window. And here I imagined that I had this remove function that worked well with the counters. The problem with counters is that it will count elements that have a value 0. But we don't want to count those. Are you going over the latest contest? Didn't attend, so can't tell. Yeah, this is the last one, the one from last night. So here we want to have a remove from a counter of and a value, and we want to decrease the value of that value, and if it is 0, then we want to delete it so that our length only counts elements that have value greater than 0. Were you not able to crack? What? Okay, so now we have our count, and the only thing that's left is to do a binary search biweekly. No, I do cracked it. I mean, I read a solution. I didn't do it by myself. It turned out that my solution was pretty close, but well, it was pretty close but pretty far at the same time. I mean, the code was close, but there was an idea that I was not gonna get. But yeah, I learned from BetSim's solution. So I'm gonna do the stream probably tomorrow. Let me. How do I? I don't know how to remove. Okay. So did you all follow the count thing? Is there any question? Yep, good. So now we do our usual binary search. So our target index is going to be, like I said, it was so let's say that we have a n. So the number of elements in the uniqueness array, as they call it, is going to be this, and then we want to subtract 1 from this and divide by 2. This is the index of our target element. And so here our invariant is going to be that count of high is strictly greater than target, and count of low is less than or equal to the target. So initially it is true because count of 0, so 0 is going to have a count of 0, and target is at least 0, and then count of n is going to be equal to the total number, and this must be greater than the target. So our invariant stands at the beginning, then we keep doing it. And so if count of mid it's greater than target, then high equals to mid, because that's our invariant, right? If count is, if it's greater than target, then that's where high has to be, and then otherwise it's low, and here we return high. And we have to pass this. All right. And we got it. We got it. 5 seconds, right? It's not. But I don't know if you can do something faster than this. I don't think so. Maybe. So, yep. Let me share this. Any questions about this one? So I couldn't take the contest. The code on this one was easier than Q3. Yeah. Yeah. Sure. And even the idea could be harder depending on how familiar you are with the concepts. Known patterns easy, bit manipulation hard. Known patterns, you mean the sliding window pattern and the kth element with binary search pattern? Yeah. BS and sliding window. Yes, you have to demystify the bit manipulation. At the end of the day, it's just a sequence of zeros and ones that you're shifting. No DP problem this time. Well, that's a good point. There's no DP problem that I know of. I mean, there are. No, I think it was a good contest because even the first two require some. So the second element, the second question was not trivial. It requires some reasoning. Problem Q3, I think it's a cool problem. Maybe Q4 was a little easier than usual. But yep, that's all I have. Is there anyone that I could rate? Let me see. Path, do you want to go online? If you have time, could you explain the daily? Okay. What was the daily? Yeah, I did many solutions for the daily in different languages. Oh, I have a lot of them. Yeah, because I think I was experimenting with the runtime. That's too many. Yeah, because I was trying to optimize a code because someone asked about the runtime in the Discord, so I was rerunning some solutions. It's not that all of them are different, but yeah, I guess this one is a solution that makes more sense. So, Oves, did you were you able to solve it, or are you stuck in some particular part of the problem? So the idea here, so you get a tree, and you want to get the sum of the distances to all the nodes from each node, and you have to use a technique that I explained. I understand it's CB, but just know how to do it not in n squared. Okay, so this uses a technique that I explained in a stream last week, I think, because there was they tend to select problems that are similar as the dailies. So I think this was repeated a few days ago. But yes, the idea is that you can, so you have a tree, you rooted at some arbitrary, so it's not necessarily, well, not necessarily binary tree. So you use this technique that I've seen it called rerouting, but you first calculate the answer. So the answer is the sum of distances to all nodes, but you do this for the subtree, right? So here you want to for this node, for example, you consider this subtree, and you want to calculate the distance to all its descendants, right? So that means that, how do you do that? That you can do that with a DFS, right? So let's say that you can do that recursively, right? So if you know what the number is for this one, so for this one the number is going to be 2, right? For this one the number is going to be 0, and for this one the number is going to be 0. So then to calculate it for this one, for each of the children, you get this number, and you add one more to the distance, equal to the number to the size of this subtree, right? So if you want to calculate this result for, let's say this is node U, for node U, you're going to add the result for node B. Let's say we're considering this child, and we want to add 1 for each node, because to count this edge here. So that means that we have to add 1 for each node in B. And so that's how we compute the sum of the distances to all nodes downwards, right? That's why I called my solution, here I call it, I call it DFS down. And here I'm doing what I said there, what I wrote there. So I calculate both the size, which is just the sum of the sizes of the children, and the rest, which is this sum of the distances downwards, of the distances of all the paths downwards. And then you do another DFS. Man, I should have joined the contest. The first 2 questions are easy, wasted potential points. Yeah, no worries. So then you do another pass, but this time you're considering a node and its parent. So let's say that this is U and this is B, right? So here this has some subtree, and this might have something here, and what else it may have. But let's say that you already know what the rest of U is, which means the sum of the distances to all nodes, but this time is to all nodes, not only the paths that go downward. So we have that from U. Now we want it for B. So we can add the result of U, but then we have to make an adjustment, because for all the nodes in here, which is the size of B, we're adding 1 more for each of them, because they're getting to U, but now we want to get to B. So we have to subtract that. So we want to subtract the size of B. But for all the other nodes, right? For all the other nodes that are not in here, we need to add 1 more, right? Because they are going to U, but now they have to go to B. So we have to add 1 more for all those nodes. And how many are there? Where there are n minus size of B. And so this is how we adjust. We use the distances from our parent to get the distance from B, right? So this is what I'm doing here. In the second one, I'm using this formula here, and that is the idea. Is it clear? It's not an easy problem, especially if you don't know this technique. Well, hope it was clear. let me see. Are there more problems that use it? Yeah, it helps. Thank you. Yes, there are more problems. Yes, last week's stream, there was a daily. What was does anyone remember what was the problem? Yeah, I think I remember. So the problem was it was called minimum height trees, and you had to consider all the nodes of a tree and calculate the height of the tree rooted at that node, which is essentially the maximum distance. So instead of the sum, so it was similar to this one, but instead of summing the distances, you wanted the maximum. And it was called minimum. So maybe I can LeetCode minimum tree, minimum height tree, I think it is. Yeah, this one, right? You see that I have a similar pattern here. So here, how often do you stream? So I do a stream for each contest, so I'm still missing the bi-weekly stream that I'm gonna do maybe tomorrow. But lately I've been doing a stream every day. I want to keep doing that, where I solve other problems, hard problems, but I try to explain them with the basics. I try. So yeah, that answers your question, solar wind. That's the other problem from last week's. Okay, so let me see if there's someone to read. Solve it by finding the center of the tree. Oh, the other one. Yeah, there are more than one solutions, but I think it's worth it to learn this technique because it can be used. So I think there's someone doing LeetCode, but I'm not sure it's on English. Well, maybe the real Raymond Jones. Yeah. Let's read him. Okay, guys, thanks a lot for watching. See you tomorrow. Thank you. Bye-bye.